In this video, I'd like to describe magnetic force a little bit more. In the previous video, I alluded to the magnetic force as like poles repel and opposite poles attract. For example, a north pole repels another north pole, and a north pole attracts a south pole. Okay, so I'm going to split this discussion up into 4 short pieces. Magnets, force on other magnets. I kind of described this previously. I just said that in order to know if something is a magnet, see if another magnet interacts with it. And that's called a magnetic interaction. Interaction just means that there are forces, right? Repulsion or attraction, or even this like special kind of it's incorrect to refer to it as a force, but it's an interaction where you get these twisting forces referred to as torques, right? Force directions, remember force is a vector, and the directions of the force vector are related in a complicated way to other details in the physical scenario, other direction details. And then I'd like to describe that there is a magnetic force on a current. In the previous video, I described that a current itself is a source of magnetic field. That is, the current is a magnet. And then it's kind of just a basic step to move up into the idea of an electric motor. Let's get going. So let's start here. Magnets' force on other magnets. That is just the basic fact of what makes a magnet a magnet. It's whether or not it participates in magnetic interactions. An example of an interesting magnet is an electric current. So let's imagine I have a wire, and on that wire is a current, an electric current, right? And that electric current could be caused by a voltage, right, in a circuit. And so this wire is definitely it carries an electric current, and it is a magnet. So interestingly, if you, for example, let's make a north pole on this side, and then I'm gonna erase these things because they're now in the way of my drawing. So let's make the situation of a magnet. So let's say that this right here is a horseshoe magnet. So it being a horseshoe magnet, let's make this the north pole and this the south pole. And in the previous video, I described that the magnetic field lines go from the north, right, emerge out of the north pole and go over to the south pole. So for example, here is a magnetic field line, and here is another one, and here is another one like this. And they're all going from the north pole over to the south pole. And meanwhile, what we have are these electrons, and they are traveling in the wire as an electric current. So let's say that the electrons are moving towards the right? And there are protons in this wire, but I'm not going to draw the protons. I'm just going to describe the fact that the electrons are moving towards the right. So the current on the wire is moving this way from left to right. The magnetism, I've given it some perspective so that the north pole sort of sits closer to you, the viewer, and the south pole is behind the wire, so it's further away from you, the viewer. And so actually, let me remove. So this is it's not the magnetism, it's the magnetic field is the white, right? So the magnetic field is actually pointing. So this is sort of a symbol for into page, right? So I've got a rightward current. Here it is. This current is heading towards the right. And I have a magnetic field that is into the page. That's what I'm trying to indicate with this circle with an X. It's sort of an arrow pointed inwards as opposed to outwards or up or left, right? Okay, so into the page, the current is towards the right. So what happens, interestingly, is this electric current is a magnet. And in this other magnetic field, due to this horseshoe, these two magnets interact. They interact with a force, and it turns out that the force on the wire is downwards. So there is a magnetic force on the wire. So let me summarize. The current is this way. The magnetism is into the page, so it's inwards. And then the force is downwards. Oops, I'm sorry. Force is downwards. So the current is towards the right. The magnetic field is in, and the force is down. And you'll notice that this is very three-dimensional. This is extremely different, right? Magnetism is very weird compared to, for example, gravity. If I have two massive objects, here's one mass and here's another, the gravitational interaction between these masses is this way and that way, right? So for example, it's attractive in this case. So gravity, if you think about it, is just along a line between the two objects, and that is one-directional, one-dimensional. And it turns out electric charge is the very same kind of thing. So what if I have a positive charge here and a negative electric charge there? This is also attractive, and the force is along the direction that connects them, also one-dimensional. Magnetism is super weird because magnetism requires all three dimensions of space. The electric current will be in one direction, the magnetic field is in another direction, and the force is yet in the third direction, and they are all mutually perpendicular. So you need left, right, up, down, and in and out. So that's really interesting. So back up here, we just described the complicated issues, right? Because the directions you require three dimensions of space to talk about this magnetism: left, right, up, down, and in and out. So that's what I mean by the magnetic force on a current. And if you have a wire that feels a force, right? So let me just say that that's the beginning of being able to engineer an electric motor, right? A motor is a situation where you have some mechanical thing that's being forced on and can move, right? So for example, an electric motor that drives a drill bit, right? So you want, in the case of a drill bit, you just want it to twist in place, and you need it to remove wood, make a hole. So that requires force. And in order to get this electric drill to work, instead of using gasoline or diesel, right, or fire or coal, we want to use electricity. Electricity seems to be so, in a sense, organized and compact and Yeah, especially if you engineer it correctly. And here is a situation where if you can have electric current and a magnet, then you get force. So if you sort of exploit this connection, magnets put force on currents, you can create the situation of a motor. And if you're really good at it, you can work for Tesla and help them make their electric motor cars more efficient. Or you can design electric toothbrushes or really nice drills and saws and other sort of house and building making equipment, right? This is that there's a lot of work to do, a lot of engineering to do. But really, this is the basic issue. Magnets put force on electric currents, and you can use that to make motors.